Let's take a look at section 7.4 where we're adding, subtracting, multiplying, and dividing radical expressions. So one of the things that has to happen for radical expressions to be added and subtracted is they have to have the same index and the same radicand. So when we look at these two square roots that we want to subtract, we notice that they're both square roots, so that means they both have an index of 2, but they have different radicands. So the only way we know whether or not we can subtract is when we look at these in their simplest form. So we're going to simplify these radicals. The largest perfect square factor in 18x squared y is 9x squared. So I put that in a separate radical and multiply it by 2y, which is a radical in simplest form. This radical is applied to a perfect square, so this radical is eventually going to go away. And then similarly, I'm going to simplify the square root of 50y by writing it as the square root of 25 times the square root of 2y. Okay, so now that we're about to simplify these, we will see that they are going to turn out to be like radicals after all, which sometimes is the case. So 4 times the square root of 9x squared is 3x times the square root of 2y minus 3x times the square root of 25, which is 5 times the square root of 2y. So this is 12x square root 2y minus 15x square root of 2y. Which is equal to negative 3x. 12x minus 15x is negative 3x. And then these are both multiplied by the square root of 2y. So notice now the radicals are like radicals. They have the same index of 2, an unwritten 2, and they both have a radicand of 2y, so they can be added or subtracted. Now we have to do a similar thing here with this cube root. Now we're interested in the perfect cube factors. So a to the 4th is not a perfect cube, but it contains a factor of a to the 3rd, which is. So a cubed multiplies by a to give a to the 4th. B cubed is a perfect cube, so that goes in this first radical. C squared is not a perfect cube, nor does it have any perfect cube factors. So that stays in the second radical where we're putting our leftover imperfect cube factors. And from this we're going to subtract 6ab times the cube root of ac squared. And notice that this radical expression is written as simply as it can be. And let's go ahead and apply the cube root to a cubed b cubed. So 7 times ab, which is the cube root of a cubed b cubed, times the cube root of ac squared minus 6ab times the cube root of ac squared. And so we see that we have 7ab minus 6ab times this radical, so that's 1ab, or simply ab, times the cube root of ac squared. And that's my final answer. So we're just continuing this process for each problem. Here, again, I need to simplify the radicals. 15 times the square root of 12 is 15 times the square root of 4 times the square root of 3. So notice 4 is the largest perfect square factor of 12. Minus 3 times the square root of 9 times the square root of 3. 9 is the largest perfect square factor of 27. Plus the square root of 25 times the square root of 3. So those are all set up to be simplified. 15 times the square root of 4 is 15 times 2 times the square root of 3. Minus 3 times the square root of 9 times the square root of 3 is minus 3 times 3 times the square root of 3. Plus the square root of 25 is 5. 5 times the square root of 3. And this is 30 square root 3 minus 9 square root 3 plus 5 square root 3. So a subtraction and an addition. And 30 minus 9, and these are all square root of 3 terms, so we can do this addition and subtraction. 30 minus 9 is 21, plus 5 is 26. So this is 26 square root of 3's. All right, so let's look at this next one, which also needs to be simplified. We have 3y times the square root of 27x to the 5th y. The perfect square factors of this are 9x to the 4th. And we're going to multiply that by 3xy so that the radicands multiply back to give that original radicand. Plus 2x times the square root. And now we're going to get the perfect square factors out of 3x cubed, y cubed. And those are x squared, y squared. And that multiplies by the square root of 3xy. So we'll now apply the radicals to the perfect squares. We'll get 3y times 3x squared times the square root of 3xy. We are assuming all variables are non-negative, which means we don't have to worry about absolute value. Plus 2x, the square root of x squared, y squared is simply xy times the square root of 3xy. And now we can multiply and get 9x squared y times the square root of 3xy plus 2x squared y times the square root of 3xy. So these are like terms. The coefficients have the same letter and variables to the same power. And the radicands and indices are exactly the same. So 9x squared y plus 2x squared y is 11x squared y times the square root of 3xy. So I simply add those coefficients and multiply the sum of the coefficients times the like radical. All right, here in dividing, we looked at the quotient rule for radicals in the previous section. So one of the things I need to do here, I have a 2 in the denominator that's not in the radical. So I'm going to look at that as simply what it is, and that's a 1/2. And then this problem is going to be easiest if I divide first. So instead of applying the cube root to the numerator and then the cube root in the denominator, I'm going to divide 16y to the 4th by 2y first. And notice how that 2 in the denominator is the same as 1/2 times this cube root that I've written in my first step. So I've got 1/2 times the cube root of, and when I do the division, 16 divided by 2 is 8. Y to the 4th divided by y is y cubed. So I've got 1/2 times the cube root of 8, which is 2, times the cube root of y cubed, which is y. So 1/2 times 2y is simply y. So that's my final answer on this one. So all of this actually simplifies to simply y. So these are my final answers. For numbers 4 and 5. All right, now I have a two-term radical expression squared. Well, just like when I'm working with polynomials, you'll recall that if I have the square of a plus b, that's a squared plus 2ab plus b squared. And that's the same format I'm going to get here. This is going to be a squared plus 2ab plus b squared. And I just have to identify what my a is and what my b is for this particular problem. A is 2 times the square root of x, and b is 7. So this is 2 squared is 4. The square root of x squared, as long as x is not negative, and we're assuming that all the variables are non-negative, is simply x, plus 2 times 7, which is 28, times the square root of x, plus the square of 7, which is 49. So this is my final answer on this one. All right, now the next problem is a problem where I have to use the distributive property twice. So I have the square root of x, and that needs to get multiplied by this two-term radical expression, square root of x minus 2. But so does the positive 6. It also needs to get multiplied by the square root of x minus 2. So this is FOIL, or the distributive property, used twice. So the square root of x times the square root of x is the square root of x squared, which is simply x, as long as x is non-negative, as we're assuming it is. Square root of x times minus 2 is minus 2 square root of x, plus 6 times the square root of x, plus 6 times negative 2, which is negative 12. So this is equal to x, negative 2 square root of x plus 6 square root of x is positive 4 square root x minus 12. And then we have another special form that we may remember working with. Hopefully you remember working with. Okay, and this is a difference of squares. So you may remember that whenever we have a plus b times a minus b, we always get a squared minus b squared. And so we just have to recognize for this particular problem, a is square root of 5x, b is 6. So this is the square root of 5x minus the square of 6. So if I square 5x, I'm simply going to get the 5x. The radical and the square cancel each other out. I'm left with the radicand, minus 36. So that's my final result on that one. Now, another thing in this section is rationalizing denominators. And that basically involves multiplying by a radical over itself. So essentially you're going to multiply by 1. So that, and you want to use the smallest necessary radical, so that after multiplying the radicals in the denominator, you get the square root of a perfect square. So the smallest radical that makes this denominator product the square root of a perfect square is for me to multiply by the square root of 2 over itself. So I'm multiplying by 1, which doesn't change the value. 1 times any number is that number. Square root of 2 over square root of 2 is 1. But I am going to change the way it looks. I'm not going to change its value. So in the numerator, when I do the product, I have 6 square root of 2. In the denominator, I have the square root of 36. And that was why I chose the square root of 2 to multiply by the numerator and denominator, because I knew in the denominator I would get the square root of a perfect square. So this is 6 square root of 2 divided by 6. The square root of 36 is 6. So we now can divide out these factors of 6. One's in the numerator, one's in the denominator. So we can divide those out. And we are left with the square root of 2. So that's our final answer on this one. All right, now we can also do something similar for a cube root. Again, we want to get, rationalizing the denominator means we want to get rid of the radical in the denominator. So we're going to do that by following a similar process. So this cube root 49 over the cube root of 4x squared is going to require the same type of work that I did in the previous one, except now I want to multiply by a cube root over itself to make the product in the denominator become the cube root of a perfect cube. So I'm going to use the smallest possible factor over itself. And I notice that 8 is a perfect cube, so if I multiply 4 times 2, I'll get an 8. And I have 2 factors of x. I need one more for this to be a perfect cube. So I'll multiply it by the cube root of 2x over itself. So this is the cube root of 98x divided by the cube root of 8x cubed. And so in the numerator I have the cube root of 98x in the denominator I have the cube root of a perfect cube, which is 8x cubed. So in the denominator I get 3x. And then I would just want to make sure that there aren't any perfect cubes that divide evenly into 98. And 3 cubed is 27, 2 cubed is 8. Okay, and this radical cube root of 98 cannot be simplified. 98 is not a perfect cube, and it does not contain any factors that are perfect cubes. So this is my final answer. I no longer have a radical in the denominator, and I have not changed the value of the radical. So my last problem is rationalizing a denominator. This has the same instructions where I'm rationalizing the denominator. And here the denominator has two terms. So I'm going to use the conjugate of the denominator, because we remember that if a radical is multiplied by its conjugate, the resulting expression doesn't have a radical in it. So the conjugate of 4 minus square root of 15 is 4 plus square root of 15. So when I multiply these conjugates, the product is a difference of squares. So I have in the numerator 11 times 4 plus the square root of 15. And in the denominator, I have the square of 4, which is 16, minus the square of 15, which is 15. So a minus b times a plus b is a squared minus b squared. So this denominator is just 1. So this expression in the numerator over 1 is simply the expression in the numerator. I don't need to actually write the 1. And that's my final answer, unless I want to multiply out. And then if I do, I get 11 times 4 is 44 plus 11 times the square root of 15. So that would be my final answer on that one.